Imagine standing at the base of like a towering 100-foot oak tree. You're holding this screaming two-stroke engine in your hands.
Right.
And with just a few, calculated flicks of your wrist, you are about to unleash literally thousands upon thousands of pounds of stored kinetic energy.
It's massive.
Gravity is basically about to take over completely. And the only thing standing between a perfectly controlled takedown and just absolute catastrophic chaos is a tiny 3-inch strip of uncut wood that you are responsible for leaving behind.
Yeah, no pressure, right.
Seriously. Welcome to the deep dive. Today's mission is highly specific and honestly incredibly critical. We are addressing you directly today.
Exactly.
If you are a student just entering the forestry profession, or, if you're gearing up to learn how to safely and professionally fell a massive tree, this is your masterclass.
And honestly, even if you never plan on picking up a chainsaw in your entire life.
Which is probably a lot of people listening.
Right, but just understanding the sheer volume of physics, the geometry, and the biological variables that go into bringing down a massive tree, it will completely change how you look at a stump in the woods.
Oh, totally. We are breaking down a massive stack of expert training manuals, professional safety accords, instructional transcripts, and just distilling all of it down into a complete audio handbook for you.
We're going to cover the absolute basics of gear and safety, then get into the complex geometry of making the cuts, and finally, the terrifying realities of managing a felled tree once it is actually on the ground.
Because bringing down a giant isn't just about ripping the starter cord and hacking away at the bark until something gives.
No, absolutely not.
Yeah.
It is a highly choreographed dance with gravity.
Yeah. And before you even look at a tree, you have to look at yourself. The absolute foundation of tree felling is uncompromising safety.
Uncompromised.
Reading through these materials, it becomes really obvious that the margins for error are functionally zero. The safety gear required isn't just like a thick coat and some gloves.
Right, you're dealing with specialized equipment designed for absolute worst-case scenarios. The personal protective equipment, or PPE, is completely non-negotiable.
And some of it is pretty intuitive, right?
Yeah, sure. I mean, you need a safety helmet to protect from falling debris. You need a mesh visor or safety glasses because, well, high-speed wood chips are essentially shrapnel.
Right.
And you need heavy-duty hearing protection because the decibel level of a professional chainsaw engine at full throttle, it'll cause permanent auditory damage very quickly.
The boots really stood out to me as well. You can't just wear standard work boots out there.
Ooh, definitely not. The manuals specify boots with an aggressive grip to keep you anchored, plus rigid ankle support.
And they have specialized protective guarding over the front vamp and instep, right?
Exactly. Plus, you need non-snag outer clothing. You really do not want a loose hem catching on a stray branch when you need to move quickly.
Yeah, but the most intense piece of gear, the one that really sounds like science fiction to me, is the leg protection.
The safety trousers.
Yeah. The manuals require pants and gloves made with, quote, chain clogging materials. I read that and just couldn't picture it. How on earth does a pair of pants clog a machine that runs at that kind of RPM?
It's actually a brilliant piece of engineering, and it's born out of terrifying necessity. A professional chainsaw chain travels at roughly 60 feet per second.
60 feet per second? That's insane.
Right. So if a blade moving at that speed makes contact with your leg, heavy canvas or thick leather will offer almost zero resistance. It'll just be sliced open instantly.
Oh, man. So to combat this, the safety trousers are packed with something else.
Yeah, they have multiple layers of loosely woven, incredibly strong ballistic fibers. We're talking about materials similar to Kevlar.
Okay, so it's essentially armor plating for your legs.
No, and that's the genius of it. It doesn't act like a shield at all. It acts like a trap.
A trap? How so?
Well, when the teeth of the chainsaw bite into the outer shell of the trousers, they immediately catch those loose interballistic fibers. But instead of cutting through them, the teeth actually drag the fibers out.
Wait, the saw pulls the stuffing out of the pants?
Literally, yes. It rips those strong threads out and instantly drags them into the internal drive sprocket of the chainsaw.
Wow.
And in a fraction of a second, these high tensile threads wrap around the spinning gear and completely choke the mechanical works.
So it forces the saw to stop.
Exactly. The fibers jam the sprocket so tightly that it brings the chain to a violent dead stop before it even has the chance to cut through the final layer of the pants and reach the operator's leg.
That is wild. You sacrifice the trousers, but you save the limb.
Exactly.
That is a staggering visual. The clothing is actively fighting the machine. And Speaking of the machine, the protocols for just putting fuel in the chainsaw are intensely strict too.
Oh yeah, you can't just unscrew the cap and pour petrol wherever you happen to be standing.
Right. The sources dictate that you have to fuel the saw in a shaded area, well away from any ignition source, using a non-spill spout.
And then there's a hard rule.
Before you even pull the starter cord, you have to move at least 4 meters. That's about 13 feet away from where you just poured the fuel.
Right.
Why so far? I mean, 13 feet seems like a lot just for spilling a little gas.
Well, petrol vapor is the hidden enemy here. It is completely invisible, and crucially, it's heavier than air.
Oh, so it sinks.
Exactly. When you pour fuel, especially if you spill a few drops, that vapor doesn't just dissipate upward into the sky. It pools on the ground.
Oh, wow.
Yeah, it settles in low-lying areas, depressions in the dirt, or in thick brush.
So if I spill a little bit on my boot, the fumes are literally collecting in a puddle around my feet.
Yes, and those fumes can travel on a light breeze. You could have a highly volatile pocket of explosive vapor 10 feet away from the actual fuel can.
That's terrifying.
If you start the saw right where you fueled it, a single spark from the exhaust or a static discharge could ignite that vapor pool. The 4-meter rule is a hard boundary to ensure you are entirely outside that invisible blast radius.
That requires a level of mental discipline that is, frankly, exhausting to even think about.
It is a lot to remember.
You haven't even started working yet, and you're pacing out safety perimeters.
Mm.
But let's get into the mechanics of actually starting the saw.
Okay.
The texts are completely unambiguous about your grip. The right hand goes on the rear handle, always, and the left thumb must be wrapped under the front handle.
Yes, under. That's critical.
I understand holding on tight, but why the strict emphasis on the left thumb wrap?
Because that specific thumb placement is your primary biological defense against the most dangerous phenomenon in chainsaw operation.
Which is kickback, right?
Exactly. Kickback is the sudden, explosive, and completely uncontrolled upward and backward motion of the guide bar.
The saw essentially throwing itself back at your face?
Yeah. The physics behind it are brutal. The chain is spinning rapidly around the guide bar. Now, the upper quadrant of the rounded tip of that bar that is known as the kickback zone. If that specific quadrant contacts an object like another branch, a hidden rock, or if the wood just pinches the chain, the cutting can't catch.
Yeah, and since it's spinning so fast.
Right. Because the chain is driven by a powerful engine and suddenly can't move forward, all of that immense rotational energy is instantly transferred backward. The saw violently levers up and back toward the operator's head or chest.
Wow. And if my thumb is just resting on top of the handle with my fingers, like a standard grip?
The handle will be violently ripped straight out of your grip. You will have zero control.
Oh, man.
But by wrapping your thumb under the handle, you create a physical lock. Your hand becomes a closed loop around the bar.
I see.
When kickback occurs, that locked grip forces your wrist to absorb the upward motion, which naturally makes your wrist roll forward.
And what does rolling the wrist forward do?
It causes the back of your hand, or your wrist, to physically strike the front hand guard.
Oh. And that guard is a trigger, right?
Exactly. That guard is not just a shield. It is a mechanical lever that activates the chain brake. When you strike it, a steel band clamps down on the clutch drum, stopping the chain instantly.
Even while the saw is flying backward through the air.
Even then. But that safety mechanism only triggers if your thumb is locked under the handle to actually force that wrist rotation.
So your body position is literally integrated into the machine's safety trigger. That is incredible engineering.
It really is.
That makes the starting procedures make a lot more sense. You can't just hold the saw in one hand, drop it, and yank the cord in midair like you see in movies.
Oh, please never do that.
Yeah.
The sources detail 2 and only 2 approved methods for starting the engine: the cold start and the hot start.
The hot start is also called the thigh or knee start. Right, let's break those down.
Yeah. The foundational principle for both methods is that the body of the saw must be completely immobilized before the engine turns over.
So how does the cold start work?
For a cold start, you place the chainsaw flat on the ground. You put the toe of your right foot firmly inside or onto the rear handle plate, basically pinning it to the earth.
Okay, right foot on the back.
Then your left hand locks onto the front handle, thumb wrapped under, of course. Then, and only then, you pull the starter cord with your right hand. The saw cannot move. It's anchored by your body weight.
But if you are deep in the brush and the ground is covered in debris, you can't always find a nice flat spot for a cold start.
Right, and that is exactly when you utilize the hot start. You grip the rear handle of the saw firmly between your knees or your thighs, locking it tightly against your legs.
And the hands.
Your left hand is again locked on the front handle in a rigid arm posture, and your right hand pulls the cord. In both scenarios, the machine is physically restrained.
Makes total sense. And once the engine is running, the rules remain strict.
Very strict.
If you take even a few steps to walk to the tree, or if the saw is just idling and not actively cutting for more than 15 seconds, that chain brake must be manually engaged. You never, ever walk with a live spinning chain.
Never.
Okay, so you're geared up, the fuel is far away, the saw is safely started, and the brake is on. Now you turn your attention to the environment.
This is where the assessment starts.
Right. The manuals are adamant that you do not just walk up to a massive tree and put the blade to the bark. You have to establish a danger zone.
Yes.
And the golden rule here is shocking to me. The safe working distance is a radius of at least 2 and ideally 2.5 times the height of the tree.
The math on that scale is pretty sobering.
Yeah. If you're felling a tree that is 100 feet tall, no one else, no spotters, no partners, no equipment should be within 250 feet of that stump.
That is almost an entire football field of required clearance.
Why such a massive radius? If I know for a fact the tree is falling north, why can't my partner stand 50 feet to the south?
Because trees are not static pillars, They're dynamic biological structures. When a 100-foot tree hits the ground, the impact is basically seismic.
Right, it's a huge crash.
Massive branches on the underside completely shatter. The tension is released explosively, which turns splintered wood into high-speed projectiles that can shoot in literally any direction.
Including straight backward.
Yeah. And the canopy can break pieces off adjacent trees as it goes down. The 2.5 height rule accounts for all the unpredictable physics of that crash.
Wow.
And if you are working anywhere near overhead power lines, the minimum clearance is twice the tree height, and you must design the felling path to direct the tree entirely away from that infrastructure.
But hold on, this raises a huge practical problem. To clear a radius of 2.5 times the tree height, you have to actually know how tall the tree is.
You do.
And I'm standing on the forest floor. I'm not carrying a 100-foot tape measure, and I'm certainly not going to climb a dangerous tree just to drop a line down. How do I know where the highest leaf is going to land?
So the manuals outline a remarkably elegant solution for this. They call it the stick trick.
The stick trick?
Yeah. It allows you to estimate the height of the tree from the ground using nothing but a straight piece of wood found on the forest floor and the geometric principle of similar right triangles.
Okay, walk me through this slowly because it honestly sounds like a magic trick. I have a straight stick in my hand. What do I do?
First, you need to create a localized right angle using your own body. You hold the stick vertically in front of your face.
Okay.
Now adjust your grip on the stick so that the distance from your eye to the hand holding the stick is exactly the same as the distance from your hand to the top of the stick.
Wait, so if my arm is, say, 20 inches long, I hold the stick so that 20 inches of it points straight up.
Precisely. Your horizontal arm and the vertical stick form 2 equal sides of a triangle. You've created an isosceles right triangle.
Got it. Then what?
Now, keeping your arm perfectly straight and the stick perfectly vertical, you walk backward away from the tree. You keep your eye focused on the stick.
Walking backward, watching the stick.
Right. And you stop walking when, from your visual perspective, the top of the vertical stick aligns perfectly with the very top of the tree's canopy.
Okay, and the bottom.
Your hand holding the stick should align with the base of the tree right where your felling cut will be.
So I just move back and forth until the stick visually eclipses the entire height of the tree.
Yes. And because the ratio of your arm length to the stick length is exactly 1:1, the geometry dictates that the ratio of your distance from the tree to the height of the tree is also 1:1.
Wow.
Assuming the ground is relatively level and the tree is standing straight, the exact spot where your feet are planted when those points align is where the top of the tree will strike the ground.
That is brilliant. You literally just stand there and say, the crown is going to hit exactly here.
Exactly here.
And from that spot, you can measure out your massive danger zone radius. But knowing the drop zone is only the first part of the assessment, right? You also have to assess the hazards within the tree itself.
Yeah, the manuals emphasize looking up before you look down.
Let's talk about a terrifying term that appears repeatedly in these texts, widowmakers.
Yeah, it's a dark term for a very common and very lethal hazard. Widowmakers are dead, broken, or completely detached branches that are just suspended high up in the canopy.
So they might have broken off during a storm months ago, but they just got tangled in the living branches and never fell to the ground.
Right, so they were just hovering up there waiting. They're massive, heavy projectiles, barely held in place by friction.
And when you start the saw,
When you start a two-stroke engine and drive a chainsaw into the base of the trunk, the vibration travels violently up the wood column.
and that shakes them loose.
Yes, that vibration is often the exact catalyst needed to shake a widowmaker loose. They fall completely silently, straight down, directly onto the operator working at the stump.
A silent killer from above. That is chilling. You also have to scan the trunk for large dead sections that could snap under the stress of the felling motion, right?
Yeah.
But the manuals also point out a hazard I would never have considered. They call it the hidden hazard. Vines. I always pictured vines as just like harmless ivy, but the texts treat them like structural steel cables.
That is exactly how you must view them. Heavy vines weaving through the canopy of your target tree and connecting it to adjacent trees are basically biological ropes.
And they alter the physics of the fall.
Profoundly.
In what way? Do they just hold the tree up?
That's one scenario. They can act as an anchor. You make perfect felling cuts, the tree disconnects from the stump, but it doesn't fall. It just hangs there, suspended in midair by the vines, fully loaded with thousands of pounds of tension.
That sounds like an absolute nightmare to resolve safely.
It is, but vines can also act like a slingshot.
A slingshot? How?
As the tree begins to fall, the vines connecting it to a neighboring tree pull taut. As the falling tree gains momentum, it stretches those vines until the tension is so great that it yanks the falling tree wildly off its intended trajectory.
Well, it swings it sideways.
Or even worse, the immense weight of the falling tree pulls the vine so hard that it violently snaps massive branches out of the neighboring tree's canopy and hurls that debris backward into the operator's work zone.
Man. So you really have to trace every thick vine to see what it's attached to.
Every single one.
So you're looking for widowmakers, you're tracking vines, and finally, you have to assess the tree's natural lean. Very few trees grow perfectly plumb. You have to evaluate forward lean, back lean, and side lean.
The lean is paramount, and it's not just the angle of the trunk. You have to evaluate the crown's weight distribution.
Like where the heavy branches are.
Exactly. If a tree has grown on the edge of a clearing, all of its heavy branches will have grown entirely on one side just to reach the sunlight. The center of gravity is completely lopsided.
Right.
That immense uneven weight dictates what kind of cuts you must make to force the tree to fall where you want it to, rather than where gravity naturally wants to pull it.
Okay, the assessment is done. You know the lean, you know where the top will land, you've checked for widowmakers. Now you have to prepare your immediate workspace.
Get the ground ready.
You clear away the underbrush around the base so you don't trip. You flatten any soft vegetation so the hot exhaust fumes from the saw can dissipate. And then you must clear your escape routes.
Plural.
Plural, yes. The manuals mandate that you plan a primary and an alternative escape route.
And the geometry of this retreat is really specific. The preferred route is universally a 45-degree angle back and away from the intended direction of the fall.
Yes.
But why 45 degrees? If the tree is falling forward, away from me, why wouldn't my safest path be to just turn around and sprint in a straight line? Directly backward.
Running straight back places you directly in the most lethal line of fire.
Really?
How?
Think about the mechanical forces at this stump. As the tree tips forward, the bottom of the trunk, the butt, is still resting on the stump. If the falling tree strikes an obstacle on its way down, or if the canopy catches another tree, the forward momentum is suddenly halted at the top. But the bottom wants to keep moving.
Oh.
The butt of the tree can kick violently backward, sliding right off the stump and shooting straight back along the felling line.
Like a massive wooden piston just firing backward.
Exactly. The area directly behind the felling cut is a highly hazardous impact zone. By retreating at a 45-degree angle to the rear, aiming for a safe zone at least 15 to 20 feet away, behind the cover of another tree if possible, you step entirely out of the path of that mechanical recoil.
Okay, so the area's prepped, the escape routes are cleared of tripping hazards. We finally arrive at the core of the presentation for our students, designing the fall.
This is the moment.
This is where you actually put the chainsaw to the wood. You use face cuts and the hinge to engineer a controlled descent. Let's start with the hinge. The sources refer to it constantly. I used the phrase earlier, but it really is the steering wheel of the tree, isn't it?
It is the single most important mechanism you will create. The hinge is an uncut strip of holding wood that you intentionally leave intact between the notch you cut in the front and the back cut you make from the rear.
So it literally functions like a fetal hinge on a door.
Exactly, identically.
Yeah.
It physically attaches the falling trunk to the stump, forcing the massive weight of the tree to follow a strictly predetermined path. It prevents the tree from twisting, rolling off the stump sideways, or kicking backward.
But the manuals give very strict golden rules for the dimensions of this hinge. It isn't just a rough estimate.
No, it's very precise.
The length of the hinge, meaning how wide it stretches across the diameter of the stump, must be 80% of the tree's total diameter.
Correct.
But the thickness of the hinge, the depth of the uncut wood separating the front cut from the back cut, must be exactly 10% of the tree's diameter.
Yes, 10%.
I need to challenge this math. If I am felling a massive 30-inch oak tree, 10% means my hinge is only 3 inches thick. Are you telling me a 3-inch strip of wood is supposed to control thousands of pounds of falling timber? How does it not just instantly shatter under that immense weight?
I know it sounds super counterintuitive, but those specific percentages are born from deep structural engineering principles.
Okay, explain.
You want the hinge to act as a steering mechanism, right? But eventually you need it to break so the tree can actually leave the stump.
Right.
If your hinge is too thin, say 5%, it lacks the structural integrity to steer. The sheer twisting force of the falling canopy will snap those fibers instantly, and the tree will fall utterly out of control.
Okay, so if too thin is bad, why not thicker? Why not a 20% hinge?
If the hinge is too thick, you encounter the opposite, equally dangerous problem. The wood fibers are too strong.
So it won't break.
Right. As the tree falls, the thick hinge refuses to snap. The falling weight will literally tear massive, deep chunks of valuable wood right out of the trunk of the tree as it crashes down, basically destroying the saw log.
Oh, that's called fiber pull, right?
Exactly. Or, even worse, the strong hinge will arrest the fall completely, and the tree will stall at a 45-degree angle, just hovering above the ground.
A hung tree.
Yes. 10% is the mathematical sweet spot. It provides just enough fibrous strength to steer the tree securely along the path, but retains enough fragility to cleanly snap when the fall is almost complete.
That makes perfect sense. So to create that 10% hinge, you start by carving out the face cut, also known as the notch.
The notch sets the direction.
Right. This is the wedge of wood you remove from the side of the tree facing your target drop zone. And to aim this notch perfectly, you use the gunning sights.
Yeah, the gunning sights are a fantastic practical feature built into professional chainsaws.
What do they look like?
If you look at the plastic or metal housing of the saw body, you will see painted or raised lines running perpendicular to the guide bar. When you are making your notch cuts, you physically align those lines like the sights on a rifle.
So you literally point them dead center at your intended target on the ground.
Exactly. Wherever those gunning sights point is exactly the direction the hinge will force the tree to fall.
This is where the curriculum gets highly technical for the students because the industry standard for this notch has evolved significantly. The manuals focus heavily on comparing two primary types of face cuts, the conventional notch and the open face notch.
Yeah, those are the main two.
There's also a brief mention of the Humboldt notch, which puts the flat cut on top and the angled cut on the bottom. That's often used on steep slopes to save the valuable wood at the base of the trunk.
Yeah, that's more specialized.
But the real debate, the core safety evolution, is conventional versus open face. Let's analyze the conventional notch first. What is it?
The conventional notch is what most lay people envision when they think of chopping down a tree. It consists of a top cut angled downward at exactly 45 degrees, penetrating about 1/5 to 1/3 of the way into the trunk.
Okay.
And this is met by a perfectly horizontal bottom cut, allowing you to pull out a 45-degree wedge of wood.
So it leaves a nice flat shelf on the stump.
Right.
But the sources are pushing operators incredibly hard to abandon this 45-degree conventional notch and adopt the open face notch instead.
Strongly pushing for it.
Yes. The open face requires a much steeper top cut, angling down at anywhere from 50 to 70 degrees. And instead of a flat horizontal bottom cut, you make an upward angled bottom cut at 20 to 40 degrees.
Right, you're cutting up from the bottom too.
So when you pull that wedge out, you're left with a massive wide open notch of 70 to 90 degrees. Let's break down the physics here. Why go through the trouble of making these steeper, more complex angles? What does that extra empty space in the notch actually buy the operator?
It buys you the most valuable currency in felling, mechanical control. And you are right, it is pure physics. Let's look at the mechanical forces at play with the conventional notch first.
Okay.
You have a 45-degree opening. As the tree begins to tip forward, the top lip of the notch swings downward toward the bottom lip. Because the gap is only 45 degrees wide, those two faces of wood crash into each other when the tree has only fallen exactly 45 degrees through its arc.
Which means the tree is only halfway to the ground.
Precisely halfway. The notch closes tight, but the center of gravity of the tree is still moving downward with immense momentum. The moment the notch closes, it acts as a massive fulcrum.
Oh, I see.
All of that falling leverage is instantly transferred directly into the 10% hinge. The hinge cannot withstand that sudden spike in force, so the fibers snap completely.
The steering wheel breaks.
Yes. From the 45-degree mark all the way down to the forest floor, the tree is utterly disconnected from the stump. It is essentially in freefall.
That sounds dangerous.
Very. During that second half of the descent, the tree can roll, it can slide, it can bounce. It is entirely out of the operator's control.
Now, let's contrast that with the mathematics of the open-face notch.
Right, because you carved out a massive 90-degree opening. The tree can fall a full 90 degrees through its arc before the top lip ever touches the bottom lip.
Which means the notch doesn't close until the tree is practically laying flat on the dirt.
The math supports that perfectly. Because the notch stays open, the hinge is never subjected to that fulcrum force. The hinge remains completely intact, steering the tree, actively dictating its path for almost the entirety of the fall.
So the tree is under physical mechanical control from the moment the wind catches it until the moment it rests on the earth.
Exactly. The open-face notch massively increases safety by eliminating that free-fall phase completely.
That is a phenomenal explanation of the mechanics. It makes the open face seem mandatory rather than optional.
It really should be.
But the texts warn that regardless of which notch you choose, there is one catastrophic cutting error you must avoid at all costs. The bypass cut, commonly called the Dutchman. What exactly is a Dutchman?
A Dutchman occurs during the creation of the face notch, when the top cut and the bottom cut do not meet cleanly at an exact, perfect apex.
Okay.
If one cut overshoots the other, even by a quarter of an inch, it creates a bypass. It leaves a deep kerf, a thin slit cut by the saw blade extending past the notch and cutting directly into the area where your hinge is supposed to be.
Okay, I understand that it's sloppy work, but why is a tiny little slit so dangerous?
Because that tiny slit fundamentally corrupts the mechanics of the fall.
How so?
When the tree begins to tip, instead of the wide 90-degree notch closing smoothly, that tiny narrow bypass slit closes almost immediately. As soon as the top and bottom of that little kerf touch, they create a premature fulcrum.
Oh.
And when that bypass closes, it instantly snaps the crucial fibers of the hinge right at that specific point.
And because it only snapped on one side, the tree loses balance?
Yes. The hinge breaks unevenly. The tree might stall, meaning it falls a few feet. The bypass snaps the hinge, and the tree just hangs there stuck. Or far worse, the uneven breaking of the hinge causes the tree to twist violently off its axis.
Throwing it completely off the intended drop zone.
Throwing it sideways or backward, yeah. A bypass cut is a lethal error. If you create a Dutchman while making your notch, you must stop, adjust your angles, and clean out the notch so the two cuts meet at an absolute perfect point before you ever start your back cut.
That transitions us naturally to the point of no return. The face cut prepares the steering wheel, but the back cut is what finally commits the tree to gravity.
The final step.
And how you execute this final back cut depends entirely on the physics of the notch you just chose.
Right. The interaction between the front and back cuts is critical. If you're using the older conventional 35-degree notch, the manual state your horizontal back cut must be made 1 to 2 inches above the apex, the pointed intersection of your notch.
Why deliberately cut higher in the back?
It creates a physical ledge or step of holding wood on the stump.
A ledge.
Remember the physics of the conventional notch. The hinge breaks when the tree is halfway down, totally disconnecting it from the stump. If the falling canopy hits another tree and pushes the trunk backward, that disconnected trunk could slide straight back towards you.
Oh, I see.
But if you made the back cut higher, the sliding trunk will slam into that 1 to 2 inch physical step of stump wood, stopping it from sliding off into your lap.
It's a physical block to prevent a backward slide. But if you are using the safer open face notch, the rules change entirely.
They do. With a 90-degree open face notch, your back cut must be made exactly level with the apex of the notch.
Level, no step.
You do not need a step or ledge because the wide notch prevents the hinge from breaking early. The tree stays attached to the stump almost all the way to the ground, so it is physically impossible for it to slide backward. A perfectly level back cut provides a cleaner, more efficient hinging action.
Let's talk about where the operator physically stands while making this final cut. The manuals talk about positioning yourself on the good side versus the bad side. How do you determine which is which?
It relates entirely to the side lean of the tree we assessed earlier. If you determine the tree has a slight lean to the left side of the tree is the bad side. That is the direction the tree's center of gravity already wants to pull it.
So the right side is the good side.
Right. You must always position your body on the good side, the side opposite the lean when executing the back cut. If the tree's wood fibers give way early, the tree will fall away from your position, not toward you.
And while making this cut, you are staring intensely at the tip of your guide bar buried in the wood, making sure you stop leaving exactly 10% of the diameter uncut. Because if you lose focus and sever the hinge entirely, you have created a disaster.
A huge disaster. Severing the hinge destroys your steering wheel. You have turned a controlled descent into a multi-ton cylinder of wood, balancing precariously on a flat stump with absolutely nothing guiding it. A gust of wind or the uneven weight of the branches will dictate where it falls. It is a terrifying loss of control.
But let's say you execute it perfectly. You make a flawless face cut, you stop your back cut at exactly 10%, and nothing happens.
It happens all the time.
The tree is perfectly balanced, it just stands there, refusing to fall. This introduces the use of felling aids, specifically wedges.
Wedges are an essential mechanical aid. They are driven into the gap of the back cut to manually lift the back of the tree.
So they act like a lever.
Yes. By driving a wedge in, you physically shift the tree's massive center of gravity forward over the hinge until gravity can finally take over. And there is a critical, non-negotiable directive here for the students. You must only use plastic or high-impact polymer wedges for this operation. Never use metal wedges.
I have to admit, that sounds backward to me. If I am trying to lift a 10,000-pound oak tree, I want forged steel, not a piece of plastic. Why plastic?
It is entirely about preserving the integrity of the chainsaw and avoiding explosive kickback. Think about the space you are working in. You are driving these wedges directly into the exact same horizontal cut where your chainsaw blade is currently operating.
Right, they're right next to each other.
If your chain, spinning at 60 feet per second, accidentally clips the edge of a plastic wedge, the steel teeth will just shave off a bit of brightly colored plastic. The saw keeps running perfectly.
And if it hits steel?
If that chain hits a forged steel wedge, the steel teeth will instantly shatter. You will ruin the chain, send metal shrapnel flying into your legs, and likely cause a violent kickback as the saw rejects the solid metal object.
So the plastic is a sacrificial tool. That makes sense. So you slide the wedge in behind the saw, and you strike it with the back of a felling axe. But the texts caution against just wailing on it. You hit it, and then you pause. What are you waiting for?
You are waiting for the physics to catch up to your actions.
How do you mean?
A tree is a massive, towering structure. When you strike a wedge at the base, you lift the trunk slightly, but that kinetic energy has to travel all the way up the trunk to shift the massive weight of the canopy. You strike the wedge, and you stop. You listen.
You're listening to the tree.
Yes, you are listening for the deep, distinct sound of the wood fibers in the hinge beginning to stretch, groan, and pop. You are feeling for the shift in momentum.
And then comes the moment of truth. The manuals state, as soon as the canopy begins to move against the sky, remove the saw, engage the chain brake, turn the saw off, and walk down your 45-degree escape route. I have to think there is a profound psychological temptation to just stand there at the stump, hands on your hips, and admire your perfect cuts as the tree goes down.
It is the triumphant culmination of your work, right? But standing at the stump is a fatal error. The sources are incredibly strict about the retreat because the environment around the stump in those final 3 seconds is chaotic and utterly unpredictable. You must view the falling tree not as a success, but as an active hazard.
Because the dynamics change so fast.
Exactly. As the massive canopy descends, it displaces a huge volume of air, causing sudden, violent wind shifts. The falling branches can snag on adjacent trees, snapping off limbs that act like loaded springs, flinging shattered wood backward toward the stump. And, as we discussed, the butt of the trunk can kick backward. You must immediately vacate the danger zone.
The sensory shift described in the materials is really intense.
It is a profound transition. You are enveloped in the deafening, aggressive roar of a two-stroke engine. Then you hit the kill switch. Suddenly, the mechanical noise is gone, replaced by the organic, terrifying sounds of the forest tearing itself apart. You hear the sharp, gunshot cracks of the hinge fibers snapping. You hear the rush of the canopy tearing through the air, and finally, the massive, seismic thud that shakes the dirt under your boots.
That's incredible.
The protocol is absolute. Kill the saw, take it with you unless it is actively pinched in the cut, and retreat down your cleared 45-degree path. But you do not turn your back. You walk backward or sideways, keeping your eyes locked on the falling canopy, ready to dodge any erratic debris.
Okay, what we've just discussed is the textbook felling of a cooperative tree. But trees are complex biological organisms, and they do not always read the textbook. This brings us to the advanced dangers section of the curriculum.
Yeah, things can go wrong.
Students must understand how to handle worst-case scenarios when the physics actively work against them. And the first scenario has a name that sounds like it belongs in a horror movie: the barber chair.
The barber chair is arguably the most terrifying and lethal phenomenon in timber felling. It happens when a tree splits vertically straight up the middle of the trunk before the operator has even finished making the felling cut.
Break down the mechanical forces that cause a trunk to just rip itself in half vertically like that.
It occurs most often in trees that have an extreme forward lean. Imagine a heavily leaning tree. The wood on the front side of the trunk is being squeezed together under immense compression, but the wood on the back side of the trunk is under immense stretching tension, trying to hold the heavy canopy back.
Okay, I'm picturing it.
When you start your back cut, you are severing the very fibers that are holding all that tension in check.
You're cutting the rope that's holding the weight.
Exactly. And because the forward lean is so severe, the pulling force of gravity becomes overwhelmingly stronger than the internal shear strength of the vertical wood grain. Before your chainsaw can cut deep enough to reach the designated hinge area, the trunk literally tears itself apart.
Oh my.
The massive back half of the trunk splits vertically up the grain, and then that massive slab of wood lavers violently upward and backward, hinging right at the back cut.
It swings up powerfully like the footrest of a barber reclining a chair.
Yes, and it does so with explosive, unstoppable force. It is incredibly lethal because the violent upward swing usually strikes the operator directly under the chin or chest before they even register that the wood has failed. It happens in the blink of an eye.
So if a barber chair is that fast and that deadly, how does a student avoid it?
It all routes back to the critical assessment phase. Recognizing the risk requires identifying heavy forward lean or signs of internal decay. If a tree has a severe lean in the direction of the fall, using a standard slow back cut is essentially a death sentence. You have to change your cutting strategy entirely.
Which brings us to the advanced solution, the bore cut. How does hollowing out the tree prevent it from splitting?
The bore cut is a stroke of engineering genius because it completely reorders the steps of the fall. Instead of starting at the outside back of the tree and slowly cutting inward toward the hinge, the operator uses the tip of the chainsaw, applying extreme caution to avoid the kickback zone, to plunge straight into the center of the trunk, completely behind where the intended hinge will be.
So you literally bore a hole straight through the middle of the tree from left to right.
Yes, you hollow it out. Once the saw is inside the trunk, you cut outward toward the front, perfectly establishing the 10% hinge from the inside out. But, and this is the crucial step, you do not cut all the way out the back. You stop cutting, deliberately leaving a thick, solid strap of uncut holding wood at the very back of the tree.
So the tree now has a perfect hinge in the front, a solid holding strap in the back, and a hollow gap in the middle.
Precisely. That back strap is now acting as the sole anchor, holding back all the terrifying tension of the forward lean. The operator can safely remove their chainsaw from the borehole. They can check their surroundings, ensure their escape route is clear, and take a breath.
And then?
Then, as the absolute final step, they position themselves safely and quickly slice through that back strap. By doing this, the operator dictates the exact millisecond the tree releases, rather than racing against the stretching fibers and hoping the tree doesn't split before they finish a traditional cut. It defuses the biological bomb.
That is an incredibly elegant solution to a terrifying problem. But let's look at another nightmare scenario. What happens if the tree falls? It doesn't barber chair, the hinge works perfectly, but the tree simply doesn't make it to the ground. It falls, but its canopy gets lodged firmly in the branches of a neighboring tree. We have what the manuals call a hung-up tree.
A hung-up tree is a massive suspended hazard. You have a multi-ton object hovering off the ground, held up by branches that are currently under immense unpredictable stress and could snap without warning at any second.
Yeah.
It is a highly volatile situation.
The training materials are very explicit about what a student must never do in this situation. These are universally banned practices. The first one, Never fell the supporting tree. I can see the flawed logic. If I cut down the tree holding it up, they will both fall down. Why is that banned?
Because you are introducing absolute chaos. If you start cutting the supporting tree, you are vibrating a structure that is holding up thousands of pounds of unstable weight. The hung tree could dislodge and fall on you while you were cutting. Or, if you manage to cut the support tree, you now have two massive, intertwined trees crashing to the ground with completely unpredictable trajectories. It is a recipe for a fatal crush injury.
Rule number 2. Never fell another tree onto the hung tree to try and knock it down like a bowling pin. Rule number 3. Never climb the hung tree to try and free the branches. Rule number 4. Never walk under the hung tree. And rule number 5, which the text note is a very common and deadly mistake. Never cut short lengths off the butt of the hung tree to try and drop it incrementally.
That last one is incredibly deceptive. Operators think the butt of the hung tree is resting on the stump. If I just slice a 2-foot round off the bottom, the tree will slide down the trunk a little bit. But when you drive the chainsaw into that angled, loaded trunk, the immense tension can cause the wood to violently snap or splinter. The tree can instantly drop and crush the operator, or the shifting wood can clamp down and trap the chainsaw permanently.
So if you can't cut it, knock it down, climb it, or cut the support tree, what are you supposed to do?
You must utilize mechanical advantage from a safe distance. If the tree is relatively small, you use specialized hand tools like a felling lever or a cant hook to physically roll the trunk off the supporting branches. And critically, you use a pushing motion, leaning your body weight into the tool. You never pull the lever toward yourself because if the tree dislodges, it will roll directly onto you. However, if the tree is too large for manual levers, you are required to use a winch.
And winch safety protocols are incredibly dense. You can't just wrap a tow rope around the bumper of a pickup truck and hit the gas.
Absolutely not. You must use a specialized hand winch or a purpose-built tractor winch. The anchor point for the winch? The tree you attach the pulling mechanism to must be located at least twice the height of the hung tree away from the hazard. This ensures the operator running the winch is standing completely outside the danger zone when the tree finally falls.
Where does the cable go?
The pulling cable, or strap, should be attached roughly 2/3 of the way up the trunk of the hung tree to provide the maximum leverage required to pull it backward out of the canopy.
The texts also mandate offsetting the winch line using a snatch block. Explain how a snatch block works in this context.
A snatch block is essentially a heavy-duty reinforced pulley. If you run the steel cable in a straight line directly from the hung tree to your winch, you, the operator, are standing in the direct line of fire. If the cable snaps under the immense tension, it will whip backward with enough force to cut a person in half.
That's horrifying.
To avoid this, you take a snatch block and anchor it to a completely different sturdy tree off to the side. You run the cable from the hung tree, route it through the pulley of the snatch block, and then run it to your winch. This creates a V shape in the cable line, physically offsetting the operator into a safe zone away from the direct line of pull.
It changes the geometry of the danger, but the manuals highlight a severe physics warning about using a snatch block. They state that the angle of the block multiplies the load.
This is a fundamental law of vector physics that catches many novices off guard. When a tension cable makes a sharp turn through a snatch block, the anchor point holding that block is subjected to the sum of the tension vectors from both sides of the cable.
So what does that mean in practical terms?
If your tractor is pulling with 5,000 pounds of force to dislodge the tree is resisting with 5,000 pounds of force. The snatch block in the middle and the sling anchoring it to the side tree are experiencing 10,000 pounds of crushing force. If your gear is not significantly uprated to handle that multiplied load, the anchor will fail explosively.
Okay, through careful leverage, or the calculated vector math of a winch, the hung-up tree is finally brought to the earth. The tree is completely horizontal, the canopy is down, the job must be basically over. But the sources point out a grim statistic. The groundwork is where a massive percentage of severe chainsaw injuries actually occur.
It is entirely a psychological hazard. The operator looks at the felled tree. It's flat on the ground. They subconsciously believe that because gravity has done its job, the danger is past. They let their guard down. But that is a profound misconception. A felled tree is a chaotic tangle of compressed energy. We now move into the phases known as snedding and bucking.
Okay, let's define those.
Snedding is the systematic removal of the lateral branches from the felled trunk. Bucking is the process of cutting the main trunk into manageable, transportable lengths.
Let's focus on the snedding basics first. The manuals describe a very specific ergonomic choreography for this. The cardinal rule is Always sned with the main trunk of the tree on your right-hand side. Why favor the right?
Because that massive trunk acts as a physical, bulletproof shield between the operator's legs and the moving chainsaw chain. You stand on the left, and you reach the saw across the trunk to cut the branches on the far side, or you rest the weight of the saw directly on the trunk to sever the top branches. By keeping the trunk between you and the blade, a kickback or a slip will strike the wood, not your thigh.
The rules also dictate that you never use the chainsaw above shoulder height, you never overreach your balance, and if the tree is lying on a slope, you must always, without exception, work from the uphill side.
Working on a slope amplifies every hazard. If you are standing on the downhill side cutting branches, you might accidentally sever a branch that was acting as a hidden kickstand, holding the massive weight of the trunk in place.
And then it rolls.
The moment that branch is cut, the entire multi-ton tree can instantly roll down the hill. If you are on the downhill side, you will be crushed flat. Working from the uphill side ensures that if gravity takes the log, it rolls safely away from your boots.
The texts also detail sweep techniques for snedding. If the main trunk is supported off the ground by its own sturdy branches, you don't chop downward. You use the top edge of the chainsaw bark to undersweep the branches, pulling the saw up from the bottom, often resting the engine casing on your thigh or the tree trunk to bear the weight. It's all about smooth, controlled ergonomics. But the real masterclass in ground management, the part that requires deep focus, comes during bucking. This is where the student must learn to read the invisible physics trapped inside the wood: tension and compression.
Understanding tension and compression dictates every single cut you make when a tree's on the ground. When a 100-foot tree lies on the uneven, rolling topography of a forest floor, it is rarely fully supported. It bends over humps and spans across dips. That bending creates immense internal stress.
Can you give me an analogy?
Let's visualize this with an analogy. Imagine a heavy log supported by a large rock at the front end and another large rock at the back end, but it is sagging in the unsupported middle over a ditch.
It looks exactly like a bridge spanning a river.
Perfect. That log is sagging downward in the center. Let's look at the wood fibers. Because it is sagging, the wood fibers on the top edge of the log are being squeezed tightly together. That squeezing force is called compression. But on the underside of the log, the wood fibers are being stretched forcefully apart as the belly sags. That stretching force is called tension.
Okay, I can picture that.
Now, imagine a completely different layout. The log is resting on a single, large boulder right in the middle, like a seesaw, and one end is hanging completely unsupported out over a drop-off.
That's the diving board scenario.
Yes, in the diving board scenario, the mechanical forces flip entirely. The heavy, unsupported end bows downward. This means the top edge of the log is stretching as it curves down, that is tension, and the underside of the log is being violently crushed into the rock fulcrum, that is compression.
So what does this mean for the operator who needs to cut that log into pieces? It sounds like you have to be a structural engineer before you pull the trigger on the saw.
You must map those invisible forces in your head because they dictate a strict, unforgiving cutting rule. You must always make your first shallow cut on the compression side of the wood to relieve the squeezing pressure. Then, and only then, do you finish the severing cut by coming from the tension side.
Let's play out what happens if a student gets it backward. Let's go back to the bridge scenario. The log is supported on the ends, sagging in the middle. The top is under compression, the bottom is under tension. What happens if I just rest the saw on top and try to cut straight down through the middle?
It'll be a very short-lived cut. As soon as your chainsaw blade penetrates the top fibers of that log, you weaken the structure. The immense compression forces the squeezing will violently snap the cut closed.
Trapping the saw.
The heavy wood will instantly pinch the metal guide bar of the chainsaw. The entire weight of the sagging tree will clamp down on your saw with thousands of pounds of pressure, trapping it completely. You will not be able to rev the engine, and you will not be able to physically pull the saw out. It is stuck until you find a lever to lift the log.
But if you follow the rule...
If you make a small undercut, first cutting a few inches up into the tension side on the bottom, and then move your saw to the top to cut down through the compression side, the log will act like a hinge. The cut will naturally fan open as the log drops cleanly downward, completely freeing the saw blade. It is entirely an exercise in reading pressure.
And the manuals specifically highlight a scenario where these pressure forces are dangerously magnified. Wind blow clearance.
Trees brought down by severe storms or hurricanes are the most dangerous environments a forestry worker will ever encounter. These are not carefully felled trees, they are violently loaded springs.
Because they didn't fall cleanly, they crashed into each other and got pinned down.
Exactly. A massive storm-blown oak might be pinned under the weight of 3 other fallen trees. Its branches are bent at extreme unnatural angles, storing thousands upon thousands of pounds of kinetic pressure. If you approach one of those bent branches and carelessly cut into the tension side, you instantly unleash all of that stored energy. The branch will undergo springback, whipping upward or outward with enough explosive force to shatter a jaw, break an arm, or violently trap the saw. You have to meticulously shave away the compression wood to slowly bleed the tension out of the branch.
The sources also warn about the root plate of a windblown tree. When a storm knocks a tree over, the roots don't cleanly snap. It rips a massive towering disk of roots, dirt, and rocks entirely out of the ground, leaving a crater behind. The manuals warn about the final cut when you sever the trunk from that massive root plate. What is the hazard there?
Think of the trunk of the fallen tree as a massive counterweight. It is physically holding that towering wall of roots and dirt down on the ground. However, the roots on the underside of that plate are often still partially attached to the earth, acting like massive stretched rubber bands.
And when you cut the trunk?
When you make the final severing cut to detach the trunk, you instantly remove the counterweight. All of those stretched roots violently contract, and that massive, multi-ton root plate can instantly snap back upright, slamming forcefully into its original hole. If the operator is standing near the hole or resting a foot on the root plate when they make that final severing cut, they will be violently thrown into the air or crushed at the bottom of the crater. The manuals mandate securing the root plate with a heavy winch cable or maintaining hyper-awareness of your physical position when separating the trunk.
Ground management is incredibly intense. It even covers lifting safety. The texts remind operators to use their legs, keep their back straight, and utilize tools like a cant hook or a PV. These are long wooden levers equipped with a swinging, biting metal hook. You use them to grab massive logs and roll them over. Why roll them? So you can cut the remaining branches on the underside without your chainsaw chain ever dipping into the dirt. Because the moment a high-speed chain hits soil and rocks, it instantly dulls the teeth, rendering the tool useless. Okay, our student has safely felled the tree, snedded the branches, bucked the trunk, and stacked the wood. The mechanical work is done. The forest is quiet. But there is one final, crucial step in the curriculum. We move to Section 7, reading the stump.
For a student learning the craft, the remaining stump is their ultimate, unavoidable report card. It is a permanent, physical record of every geometric decision made in those final, chaotic seconds of the fall.
A post-mortem of the operation. The valuable wood is gone, transported to a mill or stacked for firewood, but the stump remains rooted in the dirt to tell the tale. When an expert walks up to a fresh stump, what exactly are they reading?
Everything. The stump never lies. It reveals the exact skill level and mindset of the operator. First, you analyze the face cut section, the flat area where the wedge was removed. Was the notch deep enough to dictate the fall? Was it truly 80% of the tree's diameter?
And the bypass cuts?
You run your hand over the wood. Did the top and bottom cuts meet cleanly at a sharp point? Or is there a deep, jagged ridge indicating the operator made a dangerous bypass cut and compromised the hinge?
Then you look at the remaining wood of the hinge itself.
The hinge is the most critical forensic evidence. You check its width across the entire stump. Is it a perfectly even strip? Is it exactly 10% of the tree's diameter? Or is it dangerously thin on the left side and thick on the right, proving the operator was sloppy with their back cut, almost severing the hinge completely and nearly losing control of the falling mass?
You can also evaluate the angle of the back cut. Was it angled downward, which the texts describe as a major rookie mistake, or was it executed perfectly level and parallel to the apex of the open face notch?
An angled back cut proves the operator didn't maintain a level saw, which drastically reduces the structural effectiveness of the hinge fibers. You also look closely at the center of the stump for something called fiber pull.
What exactly is fiber pull?
In certain species of trees, the wood fibers in the core are incredibly tough and stringy. As the tree kips and falls, those tough center fibers refuse to snap cleanly at the hinge point. Instead, the falling momentum actually rips long, deep splinters of wood straight up out of the center of the stump. Or conversely, it rips chunks of wood out of the butt of the falling log.
Which damages the most valuable section of the saw log.
Exactly. If you are felling high-grade timber for milling, excessive fiber pull ruins the heart of the most valuable board feet of the tree. The manuals teach that an expert operator prevents this by making small, strategic, angled corner cuts on the far edges of the hinge area before making the back cut. This safely severs the toughest sapwood fibers before the tree begins to fall, ensuring a clean, flat break across the hinge.
If you look at a stump and see massive, jagged splinters sticking 2 feet into the air from the center, the operator failed to manage their fiber pull.
Big time.
Now, here's an interesting question raised in the materials. The sources talk about a practice called flushing the stump. This means that after the tree is safely down and processed, the operator brings their chainsaw back, turns it horizontally, and cuts the remaining stump perfectly flat, almost flush to the dirt. Why do people do this?
There are a few highly practical, legitimate reasons. Aesthetically, a flush stump looks much tidier in a managed landscape or a park. If the tree was near a logging road or a trail, cutting the stump completely flush to the earth allows heavy vehicles, tractors, or maintenance equipment to drive directly over the area without violently impacting a massive wooden obstacle hidden in the tall grass. Or, for a firewood cutter, it's simply a way to harvest one final, thick round of dense wood from the base.
But the manuals include a stern warning about doing this. You have to watch out for the mud, grit, and stones deeply embedded in the rough bark right at the ground level. The texts advise using an axe to physically chop the dirty bark away around the circumference before making that flush cut, so you don't instantly ruin your spinning chain on hidden gravel.
Yes, that is standard equipment preservation advice.
But reading between the lines, if you see a stump deep in the woods, nowhere near a trail, that has been meticulously and perfectly flushed to the ground, is it just an operator being unusually tidy, or is there a slightly more cynical reason for taking the time to make that flush cut?
There is a fantastic, cynical truth hidden in the forestry community regarding this. While flush stumps are perfectly acceptable for yard aesthetics or creating a level spot for a bird feeder, if you are walking deep in an unmanaged forest and you come across a freshly cut, perfectly flush stump, there's a very high probability that the person wielding the chainsaw made absolute terrifying mistakes.
Oh, wow.
They botched their notch angles, they created a massive bypass, their back cut was dangerously uneven, and they shattered their hinge. They did such a sloppy, dangerous job bringing the tree down that they deliberately flushed the stump to completely destroy the physical evidence of their incompetence before the foreman or the landowner could inspect their terrible report card.
They literally take the saw and erase the chalkboard. That is an incredible detail.
It is pure forestry forensics. A perfectly flushed stump deep in the woods hides a multitude of sins.
Wow. Let's zoom out and absorb the sheer volume of information we have covered. The journey we've taken today is massive. We started with the absolute, uncompromising discipline of stepping 13 feet away just to pull a starter cord. We utilized the brilliant, simple geometry of the stick trick to map out a 100-foot drop zone. We explored the complex, unforgiving physics of why a 90-degree open-face notch keeps you in absolute control, while an older 45-degree notch abandons you to free fall halfway to the earth.
It's been a journey.
We've strategized how to dodge the explosive, terrifying power of a barber chair by hollowing out the trunk with a bore cut. We've broken down the vector math of snatch blocks, and we've learned to read the invisible, loaded springs of tension and compression hiding inside downed logs.
It is a phenomenal, dense amount of technical data, but every single protocol, every geometric angle, and every safety warning anchors back to one fundamental truth: precision.
For you, the student listening to this, preparing to step into the woods, the greatest takeaway is a shift in mindset. A chainsaw is not an axe. It is not just a tool of raw power designed to hack through fiber. It is an instrument of precision. Every single cut you make is a calculated physics equation. You are engineering a complex mechanical mechanism out of living, unpredictable, heavily loaded biological material.
And that precise engineering leaves a permanent mark on the landscape. Which leads to a final provocative thought for our listeners. The next time you walk through a cleared forest or a local park where a large old tree has recently been removed, don't just look up at the empty space in the canopy where the leaves used to be. Look down at the stump. That remaining piece of wood is a permanent fingerprint. It tells the exact, unvarnished story of the tension, the mathematical angles, the physical skill, and the psychological mindset of the person holding the saw in those final, violent seconds before impact. Look at the width of the hinge. Look for the dangerous slip of a bypass. Look for the jagged splinters of uncontrolled fiber pull. Ask yourself, when you step up to the trunk with a running saw, what story will your stumps tell?
What story will your stumps tell? I absolutely love that framing. Well, that wraps up our incredibly deep dive into the masterclass of professional tree felling. We hope this comprehensive breakdown changes the way you view the woods, the physical labor, and the incredible physics involved in safely bringing down a forest giant. Stay incredibly safe out there, always respect the tension in the wood, and keep asking questions.
Thanks for listening to the Arborist podcast. Let's keep building your arborist knowledge one domain at a time. If you found this useful, please like and subscribe.